lesson 6.1, we did areas with finite sums. The LRAM, which stood for left rect area method, yes. Yeah. And RRAM and MRAM, what was M again? Midpoint, yes. Methods of approximating area under a curve led us to the next major topic, integration, also known as differentiation. I said that wrong. Well, differentiation allows us to find the slope of a curve at a single part. Integration, or anti-differentiation, allows us to find the exact area under curve between two x values. The definite integral is defined to be the limit of a certain kind of sums, and our method for evaluating the definite integral makes use of antiderivatives. Mathematicians use what is called sigma notation. The Greek capital letter sigma means summation. Very good. Have you seen that? Do you remember seeing this in grade 11 at all?
I feel like it's everywhere. It's in a lot of physics.
A lot of physics, yeah. So basically it's just a letter for, like, once you see the letter, you know you have to add them all up, right? Okay, so, and that's essentially what it's saying there. So the expression is read, the sum of a sub k as k goes from 1 to n. 1 to n. The index k tells us where to start the sum at the number below right there. So we're starting subbing in 1, and we're going to sub in all the way till we get to that high number. And in this case, n, which means it's infinite because we keep on going on forever. But say it was going like from 1 to 10, then you'd be subbing in 1, then subbing in 2, then subbing in 3, subbing in 4, all the way up to 10, and then you stop, right? So the symbol infinity, if the symbol infinity appears above the sigma, it indicates that the term goes on forever. So that's an infinite sum then. Well, if you remember from grade 11, geometric sequences, if the sequence was a ratio less than 1, that means eventually you're adding smaller and smaller and smaller and smaller terms, and then it converges to a certain number. That's why, remember doing sum to infinity in grade 11?
Yeah, but I don't remember exactly how.
So this is, again, if I were doing it in grade 11, I would bring in the calculus part of it, where this is essentially the beginning of calculus, where we're adding up all these areas forever. And if the ratio, the common ratio, is a fractional amount, then that means eventually you're going to be, because the number's getting smaller and smaller and smaller, you're adding basically nothing by the end. So then it levels off.
Okay.
Which is how we can find limits, right? So anyways, we're going to expand the following. So if you've never seen sigma notation, then you might not know how to actually do this. So again, we're starting at 1 and we're ending at 11 and we're subbing it in, and sigma means added up. So which means we're adding up 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared. Does everybody understand how I started and I ended and why it's the square and all that stuff? So you would have a calculator at this point and you just punch it all in. So I'll give you a second to punch it all in. Anyways, you get 506. So if you don't have that upgrade on your TI-84, somebody bring in a cable and maybe one day we can just, not during a class, we can come on the off day and upgrade it. Yeah, if it's important to you. Okay. So again, you could punch this into your calculator, or we're going to start at -3. So this would be negative 3 times negative 3 plus 1 is negative 2, yes? Plus negative 2 times negative 2 plus 1, which would be negative 1, plus negative 1 times negative 1 plus 1, which would be 0, plus 0 times, who cares really, but 1 plus, well, because 0 is, you're just going to get 0 there, right? And then 1 times 2, and 2 times 3, plus 3, we're going to stop at 3, right? 3 times 4, and we punch her all in, and we get, well, they probably would have this on the calculator part, yeah. But this actually you could do without a calculator. It's not even high, but yeah.
We're all about that efficiency.
Yeah. Okay, so a Riemann sum. I don't know. I just thought pulling some history into this so you can see where some of these names are coming from. Riemann sum is named after German mathematician Bernhard Riemann. Anybody German that can actually pronounce it the right way? Is that right? Bernhard Riemann? Oh, you got to have that German accent down there. That's the only thing. Bernhard Riemann. There you go. The sum is calculated by dividing the region up into shapes. You can either do rectangles like we did yesterday, or coming up is trapezoids. That together form a region, because remember when we had the rectangle, there was always that little section, it kind of looked like a triangle on top that was always left out. So a trapezoid is actually a better approximation, right? Because a trapezoid, you could have it like this, right? That's a trapezoid is just two lines that are parallel. The other two don't have to be, right? That are formed a region that's similar to the region being measured, then calculating the area for these shapes and finally add them up. So we've already kind of done Riemann sums. Because the region filled by the small shapes is not exactly the same shape as the region being measured, the Riemann sum will differ from the area being measured. This error can be reduced by dividing the region into more finely using smaller and smaller shapes. As the shapes get smaller, the sum approaches the Riemann integral. So we're going to go over how to actually find the Riemann sum. So we need to find the exact area under the curve. Here's some curve. We're going to begin by dividing the interval in a closed interval a, b into subsections. So we kind of did this the last unit where we figured out, how much the width was, but the change of x, meaning how much I'm going up by, depends on how many subintervals I want. So b would be the upper number and a would be the lower number. I subtract those two and then divide by how many subintervals I want, okay? So, and that ends up being the width or the change of x. So, for example, if we use RAM, each rectangle in the diagram would have an area of delta x times the, what did we do to find the height of the function? Remember, we had, say the width was from here to here, and then if we were doing RAM, that would be the right-hand side, and whatever that would correspond with the y value, that would be what we're timesing it by. This is ring a bell from your homework? Yeah? Okay. So, if I want to approximate the area under the curve, I take the function of x at whatever k value. So, I'm just trying to basically bring what we did yesterday into the actual exact area here. So again, the change of x was the width, and the function value was the height, and we added them all up. So that's all we did yesterday. It didn't look as fancy as this, but that's what essentially we did. So the difference here is, do you see, we're going from 1 to basically infinity. Remember, the more rectangles we have, the smaller they are, the more accurate they are, so the more exact of a value we get. So do you see, if n goes to infinity, we're basically having an infinite number of rectangles or trapezoids or whatever you have as shapes in here, and that will basically cover the area under the curve more exact. So I have a little applet to show you. Here's a theorem for you. if f is continuous on closed interval AB, then f is integrable on closed interval AB. That is the definite integral. I gotta move this over. Definite integral from a to b of f of x dx exists. So here's the definition of a definite integral. It's the limit as n goes to infinity of the summation of k is 1 all the way up to n of some function value times the change of x. So does everybody understand that this is just the width times the height, right? The width times the height. And so when k is 1, then you're finding f of 1, right? Into that. When k is 2, you're finding f of 2 times the width, blah, 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 blah. Everybody got that? So all I'm doing is I'm making this a crazy amount of rectangles by making it infinity. And so that basically, if you do that, then you will get the area under the curve, which is the integral from a to b of f of x. So why is this so big? Because I'm going to, because I want you to kind of put all these definitions and stuff on there. Okay, so this looks like a violin section. Yeah. So this is the integral symbol. Okay? This is the upper limit, and this is the lower limit. Makes sense, right? This is called the integrand. Of course, it's the function. And this tells you, because it's dx, that it's just like when we were finding the derivative d dx. It's telling you what you're integrating. Tells you what variable you are integrating. Integrand. Like grand. G-R-A-N-D. Yeah. Like grand. Okay, so we're going to turn this into this. Okay, so maybe we'll have, I'll just scroll up a little bit. Does everybody see, like it's telling you basically how to do it. They're saying, here's your closed interval goes into the integrand right here, right? Or the integral, the upper and the lower limits. So that's pretty easy. I bet you could fill that in right now. What do you get? Well, the 3 goes here, and the 1 goes there. And it's a change of x, so we're going to be integrating x. It's saying here, it's saying c, so technically I guess we should probably use c, but anyways. It's saying plug your 1 in, times it by 2, then subtract 4, and that'll give you the height. That'll give you the height there, right? This is the function value, which is this part right here. But it's telling you what to do there. Does everybody see that? So, what's my function? It's exactly what it says, right? Yeah. 2c minus 4. If you use 2c minus 4, then what would your variable be? dc. I would accept 2x minus 4 dx because it's, yeah. So the next one, do you see? What's my upper and lower limit? 8, yeah, 0 and 8. Okay, and do you see when you plug into the function value, we have 1 to whatever. Now, notice that there is a 3 over n. That should have been taken out. Sorry about that. Can you cross that out? It's not supposed to be there. Oh, well, there you go. I should have done it in white, and then I wouldn't even said anything. So I already fixed that mistake, I guess. Sorry about that. I guess I didn't fix it in my notes. Okay, there you go. So anyways, yeah. So does anybody think they know what this integral then is? It's not supposed to be, yeah. 3m squared minus 2m plus 5 dm. All right. So note, if the function is above 0, like positive, like the heights are positive, then the integral from a to b is the area under the curve of f of x above the x-axis and between the vertical lines x and a. In other words, if f of x is below the x-axis, then you have to, in order to find the area, you need to use minus the integral to find the area below the curve. So what will happen if you don't, and you'll end up subtracting the areas and you'll have a net area instead of a total area. If that makes sense. So, does everybody see we have a function here and it's saying write a definite integral for the shaded area. So, what would that be? The lower limit is what? -1. And the upper limit is 3? Yes? And our function is x cubed divided by 3 minus x squared plus 2, and we have to indicate what is the variable that we're integrating, and in this case it's x, so it would be dx. Pretty easy, right? Okay. We're getting there. Okay, evaluate the graph and using areas. So what we're doing here is we're finding the integral from 2 to 5 of the function 3. Does anybody know what the function 3 looks like?
I do.
What is it?
Constant.
It's a constant line. Very good. So if we have a line going like this, it's a constant line going like that. I hope that's what you meant, Carson, right? Because his was kind of going like this, so constant. Okay, and so we're going from 2 to 5, which means we're going from here to here. We need to find this area. I don't think I need Riemann sums or anything like that. I should be able to figure it out. And what is that? What is this width here?
4.
3. And what's this height here?
6.
3. So what's my area?
10. 9.
So it is 9.
9 what?
Well, technically it would be 9 units squared if we're talking about area. But in this case, I'm just showing you a visual of what the constant looks like. So here's a theorem for you. If you have an integral of a constant, it is just whatever that constant is times the upper minus the lower. Look at that. If I would have went 5 minus 2, I get 3. Times it by the constant is 3, and I get 9. So it's a fast way of doing it. But here's a visual of why it works the way. Does everybody see the reason why that theorem works? Is because if we have an x value of 5 and an x value of 2, the width of that is 5 minus 2, which is 3, right? And then the constant is the height.
It is the function.
So, it is the function. That's the y value. So there you go. Okay, so now we're going to do this one. This one is the integral from 3 to 6 of 6 minus x dx. So we're going to draw it. We're going to draw it. So how do we draw this? This is a line that has a slope of -1 and has a y-intercept of 6, right? So 6 down 1 over 1. Yes? Down 1 over 1. So I'm just going to take my line and draw it because it's a much efficient way of doing it, right? There we go. So there is my Yeah, because I knew if I was going to do my down 1 over 1 without any squares behind it, I wouldn't exactly see it properly. Okay, so there is my actual line. Now I need to go from 3 to 6. So 3 to 6 is from here to here. All right. So, does anybody know how to find the area of that? That's just area of a triangle, right? Yeah, so the base is 3. The height is 3. Yes? If you don't, it should be 3. If you don't know, plug it in, and 6 minus 3 is 3, right? So it is a height of 3. It's just the way I have it drawn. So that would be 3 times 3 divided by 2, because it's base times height divided by 2. So this would be 9 over 2. All right. How about this one? Yes. So you have from 0 to 4 of x minus 2. So this is a line that has a slope of 1, and it starts at -2, right? And then it's up 1 over 1. Up 1 over 1. So I'm going to just use my line again. Because I don't think the way I have this scale, it's... Oh, shoot, I'm not even... Let's see if I can... I would have been better off to take a ruler and... Something like that. There we go. That's a little bit better. Okay, so there's my line. Does everybody understand how I got that? All right. Now we're going to go from 0 to 4. Now notice that there's going to be some below and above. Oops, that's a little thick. We have that part, and then we have that part. So, hint, you can look at this as the area above the x-axis, subtract the area below. So, what's the area above? It actually is the same as the area below, right? So it's just 0. The net area would be 0. So when you look at that, you have to look at anything below the x-axis as negative. So when you're doing the integral, you'll end up getting it as a subtraction, right? Because it'll cross the x-axis as that when we're thinking about areas alone. That's all I have, right? Or is there another page? Oh, we have another page. That's what I thought. I guess I didn't have that. Oh, shoot. Do you remember how to graph these? Okay, so this is grade 11? No, grade 12. Grade 12 you learned this. And I know you learned this because I taught you. So, what did we start this out as? As a parabola, and then we square rooted all the y values. That's how we did it, right? So a parabola that got shifted down 4. Oh, actually it's upside down too, right? So it's shifted up 4. I'm looking at it wrong. So I'm just going to do a quick kind of sketch and then we'll erase it. So if 4 is right there, it's like this, right? And then if I square root it, what do we remember happens with the square roots? Yeah, muffin top. Okay, folks, I like that actually. It turns into a muffin top. So remember, we can't square root negative. So all these things underneath here are gone. Yes, remember that? And then what happens to the heights? They all get square root. So remember, wherever it was 1, it was 1, right? Remember, we have our invariant points, and then 4 became 2. Do you remember that? And then it went above like this. Remember that? You had to have that little thing over there, yeah? So now I'm going to get rid of my parabola. And that's my graph of the square root of 4 minus x squared. So we have to do this from here to here. Okay, so maybe I'll give you a moment to figure that out. I hope you know how to figure out that area.
You want to erase the original drawing we had of the...
I would, yeah. Oh, did we have a... It kind of does. Especially, oh, if the height is not as high as 2, it's even more pronounced as a muffin top, right? Sorry, so this is half of a circle. My radius is 2. So this would be equal to 1/2, because it's a half of a circle, pi 2 squared, which would be 2 pi then? A train moves along a track at a steady 75 miles per hour from 7 a.m. to 9 a.m. Express the distance traveled as an integral. Evaluate the integral. Hint. Draw a quick sketch of the velocity versus time graph. I'm going to give you a moment to think about that and sketch something. Okay. A train moves along a track at a steady 75 miles per hour from 7 a.m. to 9 a.m. Express its total distance traveled as an integral. Evaluate the integral. Okay, so it's going from 7 a.m. to 9 a.m. and it's going at a steady 75, so you could say dx. So if you forgot my little trick, if it's a constant, oh, you remembered it. You would know it is 75 times 2, which is 150. And what is that actually? It is miles, yeah.
Miles per hour multiplied by.
So, yes, and if you didn't realize, and we're getting into kind of the going forward, going backward. Remember the derivative of distance was velocity. So if we go the other way, the derivative of velocity is distance. So do you see why it would be distance? But if you forgot all that, 75 represents 75 miles per hour, and what does 2 represent? The hours. So miles per hour times hours gives you miles, right? So again, if you wanted a quick sketch, I don't think you need a quick sketch because you remembered the little shortcut, right? So, oh, okay. Well, you could. You could. No, it says hint. That was only so that you could see it's a rectangle and it's just 2 times 75, right? Maybe I'll do that really quick then. You know what I mean? You could have gone like that, right? But anyways, that's the visual of it, but you already knew the shortcut. Okay, so good news is, and when we get to the calculator section of the exam, there is what's integrals on your calculator. So here is some, we're going to do some stuff on the calculator right now. So most calculators have a built-in program, and everybody has a TI-84, so it's the same thing. Some have the upgrade so that you can actually put the lower limit and the upper limit in there. Some of you will not have that, so you'll have to do it a different way. So option 1 is to graph the function that contains the lower limit a and the upper limit b in its window and access the feature 7 and enter the lower limit and the upper limit. Okay, so let's try this. Huh? Okay, so we're going to do both options right now. So I want you to try both options because I think you need to get familiar with this. So option 1 is to graph the function. So make sure your mode is in radians first off. So then we're going to punch in the function x sine, what is it? Sine x. Okay, so then we're gonna zoom trig just to have it like you can see it properly. Okay, does everybody? I just did zoom trig to see it properly. Is everybody where they're supposed to be? Okay, so now we're going to be going from -2 to 2. So I think I can see that in my window. Yes, I'm going from If you, -2 to 2. I don't have quite, oh yeah, I have -6 to 6. So now we're going to go to calculate. Second function, calculate. Number 7. The lower limit was what again? -1. So we're going to go, lower limit is, oops. Can I actually, there, lower limit, I'm typing it in. Oh, I have to use a negative sign. Oh, you know what? I typed it in with my computer. That's my mistake. So, -1, there you go. Then the upper limit was 2. There, it graphs it for you, and then it tells you that this is 2.04, blah, blah, blah. So I'm going to put this on my thing here so you can see it. I'm not recording this. The function, if you go to Math 9, and you have what I have looking thing, how many people actually have the same that I have? Because that means you don't have the updated version. So that means you need to it's not just Riley, there's got to be more people. People aren't. So you got the good one. If you got the good one, you're smiling. If you don't, we'll have to upgrade you. So anyways, because if you don't, you have to remember the order you do this in, right? So you're going to have to do x sine x, close the brackets, comma, x, comma. Then you have to do the lower limit, which was what, -1? -1, comma, 2. And we get exactly the same answer. Do you see? The exact same answer. Do you see we get the exact same answer as we did there? Okay, I want you to try the next one. The limit as 0, sorry, the integral from 0 to 1 of 4 over 1 over x. Which one do you like better, the graph one or the other one? You like both, hey? The graphing, you do get to see it. And actually, you need to get used to the graphing one because some of the questions might ask you to interpret things. So I still say you should learn it that way. So 4 divided by bracket 1 plus x squared bracket. And then I'm going to zoom, say, standard, which is 6. Then I got to go to zoom, calculate, or second calculate, number 7. And the lower limit was 0. And the upper limit was 1. Did you get 3.14? Look at that, eh? It's pi. Huh? Oh, you got more digits, you're saying? Nice. Okay, did you do the last one? Do the graph one again. So it's going to be, clear it, e to the power. So that is that. Oops, I didn't do second function. I'll try that again. Second function, that, to the power negative x squared, bracket, zoom 6 for zoom standard. Look at that little bump there. Okay, so now I'm going to do from 0 to 5. And I know the standard viewing window has 0 to 5. If you don't do this, like, does everybody understand? In order to calculate, you have to be able to see those upper and lower bounds. So you might have to adjust your window setting to get that in. Do you know what I'm saying? So then I'm going to go to calculate 7. Lower is 0. Upper is 5. Bada bing, bada boom, there it is. Any significance of that number? There we go. And we're done. Done.